This video was requested to help re-explain some of the ideas from section 2.7 and basically give you a little more guidance as we try and talk about the ideas and concepts that come up in this section. 2.7 generically is about the ideas of rates of change and tries to show us different examples in different contexts and start to realize once again that after all this time working on the derivative and getting a lot of the reinforcement of the idea of the slope of the tangent line, we still want to have the reinforcement that this represents rates of change, but still starting to look at some specific situations to see how that could be applied. So there are examples from chemistry where the book talks about reaction rates, the rate at which chemicals can combine and that type of process. That is a rate, that is a derivative. Biological examples talking about growing cultures of bacteria, that type of population growth, that is another rate of change. There are plenty of other examples, but the one that I want us to focus on, the one I want us to be familiar with, is the relationship between position, velocity, and acceleration. If you've started to look at this section, that's what the notes really focused on, but my notes anyway, and any of the homework problems and the problems from Dr. Yee's notebook that I suggested all had to do with these three functions and their relationships. So these are common enough functions that they have their own notation, that we use S of t. S is the position of an object. We're going to use basic examples that think about objects that only go left, right, or up, down, and we're going to measure that position over t some period of time. So we'll have some units. Maybe we'll talk about the position is measured in feet and the time is measured in seconds, or the position is measured in miles and the time is measured in hours, but something along those lines. And I'll re-explain a little bit more about how this is not the same thing as distance in just a moment. But if we now start thinking about the rate of change, the rate at which position changes over time, that is the definition of velocity. Velocity as a physics definition is how far you travel over a period of time, and that's exactly what we're describing when we set up that slope of the tangent line. So instead of just looking at an average velocity, if we look at the instantaneous rate of change of this function, that is the velocity function. So this one gets labeled v of t. I'm not quite sure why they used s for position. There is some physics reason behind that, but v is a lot more clear, right? V stands for velocity. And same thing, the velocity of an object after a period of time has passed. One more, we look at the rate at which velocity changes, and that would be the acceleration. Acceleration, in physics terms, is basically the pulling force. And what we've set up with these relationships, that we had this, the position function is our original function. Velocity is the derivative of position. Acceleration is the derivative of velocity. But since velocity was already the derivative of position, this could also be thought of as the second derivative of the position function. Now, I don't want this to be an entirely just a physics lesson, but there are a few things we should talk about here. All of these are vector-based functions. The idea of a vector is that it has both size and direction. The one most of us are familiar with is the idea of speed compared to velocity. If you are traveling at 40 miles per hour, that is your speed, and that is one component of velocity, but the other component is which direction. So if you're traveling 40 miles per hour north, I'm traveling 40 miles per hour south, we both have the same speed, but by heading in opposite directions, we would have different velocities. If you're traveling north, you would have a positive 40 mile per hour velocity. If I'm traveling south, I would have a negative 40 mile per hour velocity. And that's the biggest thing that we'll see. We certainly can have objects that travel in multiple directions, but anything we look at will only be based on the left-right or up-down scenario. So in any of these situations, right has the sense of positive, left negative, up has the sense of positive, down negative. So if position is positive, that means you're to the right or above where you began. If your position is negative, that means you're to the left or down from where you began. Similar for velocity. If velocity is positive, that means you're moving at that speed in that direction. So if velocity is positive, you're moving right or up at that speed. If velocity is negative, you're moving left or down at that speed. And last, the same thing with acceleration. In which direction are you being pulled? Well, if your acceleration is positive, you're being pulled right or up. And if your acceleration is negative, you're being pulled left or down. So let's take a few more moments. We're not going to do any specific problems. You have plenty of problems both in the notes, Dr. Fay's notes, my notes. All those are good things to follow. You could always make a request and I could do some more problems in a video like this. But most of this video is just to try and get these functions a little more understanding in how they work. So let's focus on position again. And let's focus on an object. For this first one, our object only moves left-right. So with that idea, it's kind of like we're using our x-axis, and we have to have some sense of an origin. And then that entire function talks about where an object is with respect to that origin after a period of time. So for this example, let's imagine that s is measured in feet and time is measured in seconds. So if I gave you the value s of 1 equals 2, that means 1 second after the clock has started, in all these situations, t equals 0 is the moment everything begins. As soon as you start the clock, t starts moving forward, and that's when everything begins. That's why later on in my notes I pointed out, if we ever solved an equation and ended up with a negative t value, that's kind of can be interpreted something happened before we started the clock, but basically we would just reject all negative time values. That wouldn't make any sense. We wouldn't know what happened before our experiment began. So if this was my scenario, that would mean my object started here and it moved for 1 second, and after that 1 second, here is its location, and that location would have a distance of 2 feet, specifically 2 feet to the right from that origin. But now, and by the way, this is where distance starts to confuse people a little bit, because this still has some sense of distance. 2 feet is the distance from the origin, but that doesn't necessarily mean the total distance that we've traveled is only 2 feet. Let's continue with this. Let's say, okay, we knew s of 1 equals 2, and now I know s of 2 equals negative 3. Well, now all this literally tells me is that now 2 seconds after the clock started, now my object would be somewhere over here, 3 feet to the left of my origin. But how did it get here? If we knew both of these, well, I must have started going right. Maybe I kept going right and then turned around. Maybe I turned around exactly right here and then finished here. So now this would be 3 feet, but now I'm to the left of my origin. But look at how this works. Again, there's still a sense of distance. This is still telling me where I am now is 3 feet away from where I started. But how far have I traveled? Just my little basic picture here. I moved 2 feet to the right, but then to get back here, I had to move 2 feet back to the left, then another 3 feet to the left. So this does not tell me I've moved 3 feet. In reality, just following this picture, I've moved a total of 7 feet. 2 feet here, another 2 feet, then another 3 feet. That would be a total of 7 feet. So one more time, this does not represent the distance the object has traveled. It purely tells us its location relative to the origin. And the positive negative just gives us the direction from the origin. Okay, so now talking about velocity and acceleration, well, same ideas. If I'm moving in this direction, my velocity is positive. If I'm moving in this direction, my velocity is negative. So if you're ever asked which direction an object is moving, we get that directly from the velocity. If I had the velocity function, I would use the t value that we were told and just look at the sign, the positive or negative part of our answer to know, am I going right or left in that moment, or up or down in a different context. Acceleration is similar, but now let's pay a little more attention to how these relate to each other. Acceleration, the best way to understand this is the pulling force. So I had some notes talking about when you're speeding up and slowing down, and if these two have the same sign, then you're speeding up. If they have opposite signs, they're slowing down. Let's explain that a little bit more. And let's try and use my pen in the video as our object. So if I'm already moving to the right, I have a positive velocity. But if I'm moving to the right and I'm being pulled to the right, look what happens. I'm already moving this way, then I get pulled this way, it speeds me up. Now, let's think about if velocity is positive, so I'm moving to the right, but now acceleration is negative, I'd be being pulled to the left. So if I'm going to the right but being pulled to the left, I wouldn't instantly change direction. The first thing that would have to happen is I'm going this way, but I'm being pulled back this way. So as I go this way, that pulling force slows me down. Eventually, if I keep applying that force, I'd come to a stop, then I'd change direction, and then I'd actually increase and speed up. But that's the idea. The best example, and I'm a little embarrassed I didn't put this in the notes, is if we think about any object that's thrown up. If we think about that situation and we think about gravity, some of you, if you have a little bit more of a physics background, we know the acceleration due to gravity is either negative 9.8 meters per second squared or negative 32 feet per second squared, depending on if you're using metric or if you're using American units. Two quick things I should point out. I should have said this in the beginning, that just thinking about units in general, that whatever the units of distance and time that are used in the original, that these units, this divided by this would be the units for velocity, and then dividing by the time aspect again. That's why the time in an acceleration is squared. You had your velocity units, meters per second, divided by time one more time. So meters per second, more commonly written meters per second squared. And same thing with any of the other units. If velocity was miles per hour, then acceleration would be miles per hour squared. So why are both of these negative? Because gravity pulls everything down. That is a constant force, a constant acceleration that we all deal with. So if I have an object on the ground and I throw it up in the air, I'm also giving it a little bit of a directional component so it doesn't just go straight up and down. But as it goes up in the air, it'll keep going up, but eventually it would flatten off and then it would turn around and it would come back down and hit the ground. That would be the path of anything just tossed up into the air. Goes up, comes back down. Now let's think about what happens. Literally, as soon as you throw the object up, you're throwing it up, it's moving up, so its velocity is positive. But acceleration due to gravity is always negative. So literally, as soon as something leaves your hand, it immediately starts to slow down. It's going up, but as it keeps going up, it keeps slowing down, slowing down, slowing down, slowing down, until you reach this max height point, and literally at this point, velocity is zero. Anything thrown up in the air literally has this little pause. It goes up, it has this brief pause, and then it comes back down. It needs that brief pause to change direction. So at that moment, it has one tiny moment where it's stationary, velocity is zero, but acceleration is still negative. So the acceleration keeps pulling. It's pulling it down so that at the point that it stops, and now it keeps pulling it down so that our object goes down. And now as it goes down, well, it's going down, so its velocity is negative, but acceleration due to gravity is still pulling it down, so now the object speeds up. Goes down, 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 and every time it keeps bumping down, it keeps going faster, 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 until eventually we hit the ground and the object is done moving.